So today we'll be going over eigenvectors and eigenvalues. Let's start with matrix multiplication. We know that we can multiply matrices together, and so in this case, let's look at if we have a square matrix multiplied by a vector. So let's start with a 2 by 2 matrix. So this is a 2 by 2 square matrix, and we're going to multiply it by a vector. And notice that the vector has to have the number of rows of this vector has to be the same number of columns of the matrix, so it has to be 2. And so this would be 2 by 1 vector. And we see that by this produces a 2 by 1 vector as the output. GH. And so this is our, we can view this as a matrix transformation, where we take a vector, we multiply it by some matrix to get a different vector, also both in 2 dimensions. And so if we call this matrix A and this vector x, then what we're essentially doing is a transformation T of x is equal to A times x, and that produces B, which is our vector here. And so this is just a regular matrix transformation, but for certain matrices, and then for certain vectors for that matrix, what happens is when you do the matrix transformation, it produces a scalar multiple of this vector. So what I mean by that is instead of multiplying to some vector, random vector b, instead it multiplies to lambda x, where lambda is some scaling factor. So it's a scalar multiple of our vector x. And so this is what we call, this lambda is what we call the eigenvalue. Alright, and so let's do a visual for that first. So what it looks like on if you graph it, say you have some vector, right? This is your vector x. Once you multiply it by this A, left multiply by this matrix A, what happens is the vector x, the output is still some vector on this line. So for example, it could go over here. This is your AX, and it still stays on this line, or it could also go in the other direction too. Right, so I'll do a quick example with numbers. So let's say we have the matrix 4, 1, -2, 1. And then our vector x is 2, 1. So if we multiply this out, we will get, so this is 4 times 2 is 8, minus 2 gives you 6, and then this is 1 times 2 is 2, plus 1 gives you 3, and we see that 6, 3 is 3 times the vector 2, 1, which is our original vector. So in this case, we have our eigenvalue of 3. So what we say is that 3 is an eigenvalue of this matrix, 4, -2, 1, 1, and we see that 2, 1 is our eigenvector. So eigenvector are specific to each eigenvalue. So we say this vector 2, 1 is an eigenvector of this matrix corresponding to lambda equals to 3. And if you have a different eigenvalue, lambda equals something else, then you will have different eigenvectors that correspond to that eigenvalue. Alright. So now that we have that, let us see how this works in a 3 by 3 matrix. We want to see if this vector 0, 1, 2 is an eigenvector for this matrix. So again, we do the multiplication. Let's see if we can do this. So 5 times 0 is 0, everything else is also 0, so this is going to stay 0. This is 0, 4 minus 2 gives you 2, 0, 2 plus 2 gives you 4. And we see that 0, 2, 4 is 2 times 0, 1, 2, our original vector, which means we have a eigenvalue of 2 here for this matrix, and 0, 1, 2 is an eigenvector corresponding to lambda equals to 2 for this matrix. Alright, so now how do we find these eigenvalues? So things, eigenvalues, it's not like every number is an eigenvalue for any matrix. Certain matrices will have certain eigenvalues, and so we need to find that. So let's derive an equation that will help us solve it. We start with our definition of our eigenvalues and eigenvectors. We can write this right side as lambda ix, where I is the identity matrix. This shouldn't change anything because identity matrix times the vector x will still give you your vector x. Now we're going to subtract that to one side. And this O or 0, this is your 0 vector, not just a regular scalar 0. And so once you have that, what you're able to do is you can kind of imagine like factoring out the x. I guess it would be like right to multiply, right? So it would be a minus lambda I right multiplied by x. Should give you your 0 vector still. And so we have this equation. We notice that a minus lambda I, this is a matrix here. And we have our vector x, right? And what we're saying is that when we take this matrix multiplied by this vector, we get our 0 vector in return. And if you think about it, that means our set of vectors x here is our null space of this matrix, right? By definition of null space. And so if we want our null space to not just be the 0 vector, if we want real eigenvectors that are like with real numbers that are not 0, we need x to have non-trivial solutions, which means that this matrix here has to be not invertible by the invertible matrix theorem, if you remember that. And so if this is not invertible, that means if this is not invertible, then that means the determinant of the matrix is 0. That is also part of the invertible matrix theorem. So that means for x to be an eigenvector for this lambda value, we need determinant of a minus lambda I to be equal to 0. And so this is called the characteristic equation of this matrix, and this will tell you the eigenvalues. So let's do an example. We'll see what a minus lambda I really is here. Let us use this. So a is going to be equal to 2, 0, 1, 3. It's going to be a 2 by 2 matrix. And so if we have a minus lambda I, right, so we have 2, 0, 1, 3, and the minus, so the identity matrix would be just 1, 0, 0, 1, right? And then if you imagine lambda times all this, then it becomes lambda 0, 0, lambda, like this, right? And so we can subtract this. We get 2 minus lambda, 0, 1, and 3 minus lambda. And so now we know that the determinant of this has to be equal to 0, and when we solve that, we get our lambda values, our eigenvalues. And so determinant of a 2 by 2 matrix, if you remember the formula, it is these two minus, so this times this minus this times this equals 0, or equals 0 here. So 2 minus lambda, 3 minus lambda, minus 0 times 1 gives you 0. I will just negate both of these, right? Because negative times negative gives you positive. Probably just easier to look at. Right? Minus 0 equals 0, so this whole thing is equal to 0. So we see that in this case, lambda equals to 2 or 3. That means our eigenvalues are 2 and 3 for this matrix. And so now we're going to use that to find all the eigenvectors corresponding to each eigenvalue. So let's start with lambda equals to 2. What we do is essentially plug it back into this variable right here, this right here, because we said, I erased the equation, but we said a minus lambda I times x equals to 0. So now we can find a minus lambda I, and then we can solve for our eigenvectors x. So a minus lambda I is equal to, 2 minus lambda, so since we're lambda is equal to 2, 2 minus lambda is 2 minus 2 gives you 0, 0, 1. You have 3 minus 2 gives you 1. And so this times x is equal to 0. So to solve that, we can do our row reductions to get it into reduced echelon form. So in this case, well, we already have a 0 row. Technically, I guess you just flip the rows. It would be like 1, 1, 0, 0. And from these, we can get some equations. So we can get x1 plus x2 equals to 0, and then the 0 row. And so what this tells you is that x1 equals to negative x2. And so our solution to the our solution for x, the eigenvector x, is x1, x2, which is, plug that in, negative x2 times x2, factor out the x2 for negative 1, 1. And so what this is saying is that x2 is just a random variable. It can be any real number. And that, as a scalar, times this vector negative 1, 1 will give you an eigenvector. In other words, we have an infinite number of eigenvectors, and we can say that negative 1, 1, this vector is a basis for all of those eigenvectors, for the set of all eigenvectors. And so if you're to graph it, what that means is negative 1, 1 looks something like this, right? And so that means x2 times that means anything along this line will be an eigenvector for lambda equals to 2. And so what that means is if you take A, or matrix A here, 2, 0, 1, 3, multiply by any vector along this line, you will always get some vector still on this line. Alright, and let us do the same, but for lambda equals to 3, our other eigenvalue. Here's this. There we go. So lambda equals to 3. We have 2 minus 3 gives you negative 1, 0, 1. 3 minus lambda gives you 0. And so here, what we get is that, well, we have some equations. So we have, let me see this right. 2 minus 3. Yes, okay. So negative x1 is equal to 0, x2, or sorry, x1. This, okay, let me row reduce this, sorry. So this row reduces to, we notice that these two are essentially the same. So this is just 1, 0, 0, 0. And so what this says is x1 equals 0, and then x2 is 3. And so what to do with that, we say that our vector x1, x2 is 0 and then x2. Factor out the x2, we get 0 and 1. So now we have 0, 1 is our basis for all the eigenvectors corresponding to lambda equals to 3. So graphing this, what happens is that if we graph 0 and then 1, so it looks like this. Alright, so that means any vector along this line, you multiply A by that vector, you'll get a vector back on this line. And specifically, it will scale it up by 3. So for example, 0, 1 will get scaled up to 0, 3 over here. Alright, okay. So now we can talk a little bit about the applications of eigenvectors and eigenvalues. So it's used in many different areas. One, for example, is something called principal component analysis. Another key application is in Markov chains. So a Markov chain is essentially a way to model a situation in order to predict like probabilistic events, where the future events are based on only the current state you're in. So let's do a simple one. Let's say we have two populations of diseases, disease A and disease B, or bacteria, I guess. So A and B. And they're kind of trying to convert each of them into themselves, right? So let's say at every unit of time, 20% of units of bacteria A gets converted to B, and 10% gets converted from B to A. Now let's say they both start at the same amount of bacteria, like 150 each, right? What do you think will happen in the long run, after you run for multiple units of time? You might think at first that because the 20% is more than 10%, that eventually everything will become bacteria B, but that is not the case. So let's do a couple examples. If we start with 150 and 150, we can calculate that after 1 unit of time, for A, you retain 80%, right? So you have 0.8 of that 150, and then you take 10% from B. So you have the 0.1 from B, and for B, you retain 90%, and then you add in your extra 20% from A. And so if you do this, I believe you get 0.9, should be 135 and 165. And you see, so you get slightly more B now, right? But what if the population was at, instead of 150, 150, let's say it was at 50 and 250, what happens then? Let's look at B. B, you get the 0.9 retains from the 250, and then you have the 0.1 from that 50, and this adds up to 225 plus 5, so you get 230. And so you see, you went from 250 to 230. You went down in bacteria B. So obviously, it doesn't go all to bacteria B, which means there's some equilibrium in the middle, where at some point you have some A, some B, and then after a while, when you keep running it, no population changes. And so we're looking for that equilibrium, and that's where eigenvectors come in. Right, so we can graph this. So these populations sum to 300. So we're going to be on this line here, where this is 300 and 300. Let's say we start off at the 150. So then we start off in the middle right here. And this is A, this is B. Population A, population of B. And so we slowly move this way, but it stops somewhere here along this line. And so essentially what we're saying is that, and so we said this is essentially a matrix multiplication, right? So if 150 is our population of A, this is our population of B, then we essentially are doing 0.8, 0.9, 0.1, 0.2 times PA, PB. And we see that 0.8 times PA, 0.1 times PB, 0.9 times PA, 0.2 times PB. And so this gives us our new PA and PB. So we can represent this situation as a matrix multiplication. And what's going on is that once we multiply this by some vector here, it stays as the same vector. If you're staying as the same vector, that means we have an eigenvalue of lambda equals to 1. And so now we can solve for this vector here. You can also do it with just pure algebra, but I want to show it with eigenvalues. So remember A minus lambda I, so we subtract lambda I, which in this case is just the identity matrix. So alright, so slight mistake, we want to solve below 0.9 and 0.2 so that they match up to 0.2 PA and then 0.9 PB. And so we can minus our identity matrix I, which then should give us negative 0.2, 0.1, 0.2, negative 0.1, and so we get a 0 row, and then we see that 2x1 minus x2 equals to 0, so x1 is equal to x2 over 2. So that means x1 is going to be half of x2, or bacteria B. So we can split it as 100 for bacteria A and 200 for bacteria B, since that's a 1:2 ratio. And if you multiply this matrix by 100, 200, you'll see that you should retain 100, 200. And so this is an example of a basic Markov chain, but eigenvectors and eigenvalues are also very useful for even more complex Markov chain as well. Thank you.